Well, hello, everyone. We'll get started. Yeah. Feel free. I don't know much about the previous tutorials. This one is going to be a hands-on. So if you have a computer, that would be much better. You'll get much more out of this. It's mostly exercises for you to implement. As a disclaimer, if you guess by my accent, I'm Spanish, so now it's my normal siesta time based on my genes. So you will be the ones who are doing all the work, and I will just be giving the exercises. So, cool. Just a quick question before we start. I had to make a guess on which kind of audience I'll have here today when deciding how to deliver, how to present this, and which things I could assume to be known and which things were not. Just as a heuristic, how many people here are more or less decent C programmers or another low-level programmer? Can I see hands? Okay, few of you. As a disclaimer, yeah, I'm not assuming that, and yeah, I would say most of the people, for what I've seen, it was not the case. So yeah, that for the people who are good C programmers, I think this is going to be a bit slow. I will be talking, and particularly if you know more or less how pandas works internally, this is not going to be like very useful in many of the parts of this tutorial. Hopefully you still can get something out of it, like in the general idea on how this is being implemented. So cool, just to get started, I guess you are mostly interested in extending pandas in Rust, or maybe you already know NumPy and it was the only other tutorial happening at this time. So whatever is the case, why would you like to extend pandas with Rust? I mean, you might have use cases yourself, but here are just some of the examples, some of the ideas behind presenting something like this. Like pandas can be just too slow in some cases. That hopefully will keep changing, will keep improving the library. But yeah, some things can be still slow. Some things cannot be implemented. Some things, like maybe you use a lot some patterns that actually you can implement better as a whole, like better in terms of performance. Here you have this example. For example, if you are familiar with this in pandas, you have the n largest. It's just like sorting, but only care about the first n elements of the sorting. So this can be much faster than sorting everything and then discarding everything that you didn't care about. So in some cases, in this particular case, pandas already provides a function to be faster, to be able to do a sort values and a head. But in some other cases, you might have patterns that just don't follow into that category, and it's convenient for you if you need speed to implement an extension, and particularly Rust extension. And the reason for Rust here is speed. And also, you might have data types that are not like the normal, let's say, the standard data types. Maybe you are working with integers, floats, that's the most common ones. But in some cases, you might be working with different things. You might be working with proteins, you might be working with molecules, you might be working with images, particular kind of images, or geographical data, so many things that it might or might not be supported. So you might want to implement your own library on top of pandas, just extending and using pandas as a framework, but then implementing your functions for your specific data type. So that's some of the reasons that I think this talk should be, or this tutorial should be relevant. So as I said, we are gonna be mostly doing exercises. The idea, if you read the abstract, is that you should have a Python environment and also a Rust environment. Hopefully that's the case. That would be much more interesting. And yeah, we'll start very small and keep building. Like, as I said, I don't want to make this like as a tutorial based on many assumptions on you knowing many things. So hopefully for the people who are just familiar with pandas and Python still can follow this and and go along. So yeah, I'll just give like few minutes. This is a kind of just like to get a bit of context. The idea here is like we want to implement a function that pandas doesn't natively implement. That it's like count the number of fives in a number. So you have a number, you can get its decimal representation, and in its decimal representation there would be a certain number of 5. You have 4 examples here, so the number 1 of course doesn't have any 5 on it, but the number 5 or number 15 or number 50 would have 1, and the number 505 would have 2 of them. So basically we want to implement this function, and we want to implement it in the context of pandas. So yeah, if you have, I mean, feel free to use Jupyter if that's what you use, or feel free to just create a script and run it. But the general idea, and we'll keep building on top of that. So if you implement this function in the next exercise, you already will be using this function as part of pandas. So yeah, if you don't follow these exercises, you probably won't be able to follow any of them. Or you can be very fast and implement all them at the end. But I guess there won't be many questions at this point, but for the rest of the tutorial, feel free to interrupt me, just show hands, and since we're recording this, please wait until you get a microphone so your question is also recorded and people watching online have more context. Can you just show me a hand when you are done with this function? Okay, a few of you. I'll give a couple more minutes. Like if you need help, also feel free to ask the person next to you whether it's setting up the environment or implementing the function. Yeah, this one should be simple if you're familiar with Python. Cool, are we more or less done? Let's go on. Cool, so this is my solution. Of course, it's not the only solution. Like in most cases, you will have alternative implementations that do the same, but I think this is a reasonable one. We just convert the integer as a string that basically will cast and will get our decimal representation as a string, and then we just use the Python method count of a string to get how many cases the 5 is there. And as you can see here, I have a series. I just made up a series with the numbers that you had in the example. And we have the apply function, and apply, what it will do is apply this function to every element in the list. In the series in this case. So if you run this, you should be able to have like the numbers from the previous, saying that 1 and 2 have zero number 5s on it, and 5 has just 1, and 505 has 2. That should be it. I guess it's simple, and I think this makes a point, I would say, that we can already extend pandas, like without anything fancy, with no Rust, with no anything, like extending pandas, just extending pandas is pretty easy. You just implement a function in Python and you can just apply and that, yeah, should pretty much work in many cases. But this might not be the fastest implementation, and we'll see a bit more later. Are you okay? Does anyone need a bit more time with the solution? Are we fine? Cool. So next thing about APIs. So we've seen that when we're designing like extension for pandas, we in a way are becoming a pandas developer ourselves. So the general idea here is that then we can have users. Maybe the user is only ourselves. Like if we just implement this function for count 5 and we apply it, and this is part of our internal code, and when nobody else is using this code, that's pretty much the end of it. We probably don't need to think that much other than our code, but if we imagine that other people can be using this code, like then we need to start thinking about API design, how we allow users to use our extension. And in this case here, we made an assumption. Our assumption or our decision is that this lives as a function. You might have to import it from somewhere, and if you want to use it, you need to provide it to apply. That is something that pandas design it this way. We can use it or we cannot use it, but we have different ways. And a different way is the pandas. Pandas provides a way to extend and implement functions that behave a bit more like the pandas functions themselves. And this is would be the pandas extensions, what we usually would call the accessors. And the accessors have this, what you're seeing here at the very bottom, that's what the final users would be using. As a developer, we can implement things in certain way, and then pandas will make these counters accessor, that's the name how we call it, available, and these counters will have any function that we want to implement on it. So if you think about the string operations in Python, they are implemented in this way. We have the .str, and the .str has a lot of functions or lots of methods, and they are all grouped, to say, in this namespace that it's this str, that it's just like let's say an empty class, or not empty, it has attributes, but a class that pretty much doesn't do anything other than letting us accessing the functions that it contains. So pandas does that internally, and also pandas allows developers of libraries to extend pandas in this way. So you can just create your library and then register in certain ways. This is what you need to do now. This is like the exercise. And if you register them this way, then your users would be able to use this. Counters might not be the most beautiful name for an accessor. We usually use shorter names like str or dt for dates, but there might be others. Like you can use anything. And as I was saying that you can implement extensions in pandas. Maybe a use case is to use data types that represent molecules, that might represent molecules, and a string representation in a binary representation that would be much faster. And then any function that you implement that applies to this particular data type, you can use an accessor to implement all these functions in a namespace. So you could be able to say my data frame .mol for molecule and count the number of atoms, or count the number of nodes, or count whatever you want to call. So yeah, I didn't provide much information here, but you have this page on extending pandas. I assume any search engine that you use, like you should be able to find, I don't know, maybe if you're based in the south of China, you find something about animals, but I assume for you it should be pretty easy to read our documentation and see an example on how this is implemented. This is pretty simple, so yeah, I'm gonna give you a few minutes, and if you can get like this example, this function that we implemented as using this pandas API. And also when you're done, if you can just show me a hand or something so I have an idea on how much time do you need, that would be great. Cool, I see some of you finished. I think I'll probably continue and I'll show you the example. You can, like the example, the solution. If you didn't finish or you didn't figure out, feel free to ask me any question if this is not clear or you have anything. There might be other possible solutions. Also, I think in the documentation you will have an example, at least first, on data frames. So maybe you implemented this to a whole data frame instead to a series. Like there are different ways. It's like just a decision. For the exact thing here, this is a series, so you will have to apply it to series, but there might be different ways. And also for the exact, I'm using apply here. You could loop. You could use other approaches. So yeah, like if you have something different, it doesn't mean that it's wrong, but here you have a sample that should work. Good, and as I said, like you'll need this code to continue with the next exercises. So if you didn't finish or something and are interested on continuing with the exercises, you might want to copy the solution. Okay, I don't see many people copying, so I'm gonna go for the next exercise. And I think this becomes a bit more interesting. Now we've got an implementation, and yeah, as I say, like Rust, the reason for Rust, we're already extending pandas. So if you want to extend pandas and you don't have a problem with performance, if things are working fast enough for your use cases, I think we're done. I don't think there is any good reason to just do something fancier unless you really feel like it and you like those things. But yeah, like if your data set is 100 samples, I don't think you need anything more than that. You can extend pandas, as you've seen, like with just apply and your own functions, or you can extend pandas providing this API that it's like the pandas way of doing things. Like whether it's a good one or not, I won't enter in that discussion, but like it's the way that pandas users are used to implement, to use those things. So, but for the cases that things are not fast enough, then things become way more tricky. So, and on this trickiness, we'll start by making our example like a bit like compute more things, more than these 4 numbers that it's gonna, of course, be pretty immediate, just 4 numbers. So yeah, I'm using 10 million here. You can use another one, but at least if you use the 10 million, you of course can have a computer that is much faster than mine, or even is lower, even if this one starts to be a bit old. So I guess it might be more in the faster side of things. But yeah, feel free to use any example that you want, but we have this extension, whether you want to use apply or this pandas extension API, like that should be the same in terms of performance. So use whatever it's more convenient for you. But whenever you find, like, whenever you are able to replicate this and time whatever you want to time on this function, like the exercise here is to try to find something to make this faster. Try to think a bit and find solutions. And I think there are some options there without doing very complicated things to try to speed up things. And this time I'll be asking, like, I won't just expect you to wait for, like, to complete. I would expect you to give me some of the solutions that you find and how fast they are. So feel free to, think about them and also to experiment them and implement them. Some of them can be fast. So yeah, in this case, when you try something, if you find any approach that you think should be faster, whether it's faster or not, just let me know and we can discuss it. I would like to know what are people's thoughts. No, there is no link to the material. Well, I could share the slides, but yeah, there is no material. You're just supposed to do the exercises and build the material yourself. So. Anyone could try any other implementation that is faster or slower? Okay, can someone? Yeah, sorry, there. Yeah, just wait for the mic, please. So we'll.
Yeah, so I've got a slower one, which I didn't really expect, but I guess it's a Python thing. So I went with a loop, dividing by 10 and taking a modulo of 10, and so counting the individual digits, and it turned out to be slower. So yeah, there it is.
Okay, yeah, that's a good test. Yeah, and I think it's interesting. It will be relevant on when we move to the Rust world. Anyone else? Any other implementation? That was clear. Was that clear? If I understood correctly, the idea is like you convert to a string and then you iterate on every character and you check if there are 5. Is that, or you do it?
Yeah, so I just wanted to go with integers all the way. So I'll just go digit by digit and divide by 10 and
I see.
Take a modulo of 10 and compare it to 5.
Okay, I see.
So using integers instead of strings. Well, I don't know if it really makes sense right now.
No, it makes less sense, and yeah, of course, in practice, I think I know why it's not faster, but yeah, I think it sounds like a very reasonable approach. Yeah, there is someone. You got your mic? Okay, cool.
I'd assume that the expensive part is casting each cell to a string, so I'd rather cast the whole column at a time and then work on a string column instead.
Yeah, one column, one cell at a time, you mean? Did I understand?
Your first implementation would convert each value to a string separately, and I'd rather have the whole column converted at one time, like as type string, and then work on that instead.
Yeah, did you try that, or?
Yes, seems to be factor 2 faster.
Factor 2 faster. Okay, that's cool. Can you develop a bit more on the solution? Exactly what, just for everybody to follow. Yeah, can you expand on exactly like the implementation, like what you're doing?
So I changed the implementation of counters. So what you have this accessor, and you can use the self series in your case. You can cast series.astype string to it, and so then any other operation that you apply on the series then is applied on the string series.
Okay.
But on the other side, you have a copy of it. Yeah, depends on what you want.
And what's the speed improvement? You say 2 orders of magnitudes faster, or?
No, not 2 orders. It's only a factor of 2 faster.
A factor of 2 means half?
Yeah.
Okay. Sorry. Yeah, that's good. Yeah, good solution. Anyone else? Any other solution that you? Okay, not sure if anyone is still trying things, but maybe I can show things that I tried. And I think I tried your same solution, but with different results in my cases. So I tried, well, the first one is the one that I shown, that's basically using apply. And then I tried and in my computer, and you might get different results, and my results are not very intuitive in my computer, so I'm not sure really what's going on in this case. But yeah, what I'm doing is just to convert data to a string, and then for each string I call the pandas string counter, like the count in a string. So, but that happened to be slower, even it can seem that usually like in general, and I'm not sure if you're familiar with this, but in pandas, if you implement your own things, it's slower. If you use the pandas ones, that's usually what we call the vectorized versions, and we're gonna see much more about this. That's kind of like the core of this tutorial. Like, it's usually faster. So if you have something like a function that pandas is implementing, it's a sum, it's gonna be kind of fast. If you just iterate over your series and you do the sums yourself, that's usually much slower. That's what you would expect. So in this case, I think it would be intuitive that it was faster. It's not in my computer, and as I say, like, you might have different things, but I guess they should be somehow consistent. For what we're seeing, it's not. Like you say, it's 1 order of magnitude faster for you. For me, it's one order of magnitude. No, sorry, like half the speed. For me, it's double. And then I tried like a different version of it, that it's, instead of using the traditional string type in Python, that it's like in pandas, that it's using Python strings. It's actually using arrow strings. And we are going to get more a bit later in this difference. I'm happy to provide more information if people are confused. But the way that pandas represent things internally, it can change for the same type of value. And a string, you can represent it in different formats. Like, some of the parts would be common, but in some cases it would be just like a Python object, like a Python string object, that when you go to the very details of memory, how this is represented has some implications. It's representing in certain assumptions, certain decisions, certain structs. And then you have the arrow implementation, that it's an implementation that it's been more designed for this. Like, Python has never been designed as a data language. It's been designed for many things and has like excellent like use cases where it's ideal, but not for data. For data, it makes certain decisions that it's making things just slower. So yeah, I tried this, and the arrow implementation I would expect to be faster, and it was faster, but it was still slower than apply. I can guess why it's the case, but yeah, that's good that we've got the alarm clock since it's my siesta time. But cool. So yeah, like, I'm not sure what's the takeaway for you here. I would say that, yeah, like, we could consider that actually apply is just fast. So we can say like, okay, like, we can just implement things in Python. We are happy, and our other alternatives, at least in my example, for you it was a bit different, but seems to be slower. But I wanted to try something else, and that was polars. So I gave a try with polars, and this is where I got 1 order of magnitude faster. So it seems like really our apply implementation is not that great. We can do much better. And yeah, there might be reasons for that. So let's say my takeaway here is like, okay, I cannot make pandas, at least in an easy way, faster. But possibly, like, if other tools can do it faster, I think we should be able to also do faster. There is no reason for that. So of course, one alternative is just to stop using pandas and use polars. Like, that will save you from implementing extensions. In some cases that's reasonable, in some cases that's not reasonable. You already know pandas, or your company is using pandas, or you prefer the stability of pandas, because pandas is gonna be a bit more stable since it's a much older tool, and we take care much more about backward compatibility than polars, that it's kind of like a newer project, and it's still developing very fast and focusing on innovation and having a good API much more than in backward compatibility, because as far as I know, there is not too much polars code out there. So yeah, that hopefully motivates a bit like the reason why we're here. Like, we still want to use pandas. We know that we can do faster, much faster than implementing with apply. So Rust is going to come to the rescue, and of course it's not only about Rust. There are other things that we can do. If you're familiar with Numba, for example, Numba is a just-in-time compiler that it's designed to take a Python function that the one we implemented. You should just be able to use a decorator on it, saying like, okay, I want to just-in-time compile this one, and it should speed up things like pretty easily. But this is not what we're going to see. This would be a Numba Amba tutorial if that was the approach that we were taking, but surely it's an option, and in some cases it might make more sense because it's just easier. Just install another dependency, you just decorate your function, and you can get up a solution that it's fast enough for you. So if that just works, I would say like performance should in general come after simplicity. If you have two solutions and you lose a bit of performance that you don't care that much, and you get a much better, much simpler solution, I think that would be good. And also other solutions, I mean, I'm going to talk about Rust here. I have some reasons, and the reasons are kind of like these bullet points. But of course, you can do the same things in C, in C++, in Fortran, and yeah, like there is no particular reason why pandas can be extended in Rust and cannot be extended in C. Actually, C is a much more natural language to use. C was designed to be like the language to extend Python, or in certain way could be designed like as Python as the language to extend C when C is not that needed because of performance. So, but yeah, I have some reasons, at least personal, and as I list here in the slides, this is a personal opinion. Of course, you can disagree. You can have your reasons to hate Rust. Rust is not particularly easy to learn language. I think that's the main drawback that we found here. There are a few concepts that I think are extremely smart and are extremely well designed, but not necessarily easy to understand initially. I think when you start to be familiar with them, they make a lot of sense, and they save a lot of time in many ways, and a lot of pain from the development of software. But yeah, of course, doesn't need to be your first choice. But if it is, and here are some of the reasons, I'm gonna list them quickly. I think it's more readable than most of the languages that work at that level. When I'm saying it's more readable, I don't mean more readable than Python. I think Python is more readable kind of by design, and it made certain decisions, and the nice thing about Python is that it's making lots of decisions for you. The bad thing about this is like on these decisions come at a cost, and the cost is in general speed. So when I'm comparing here, I'm assuming that, yeah, Python, we already tried, we already extended with Python, but it was not fast enough, our implementation, and for whatever reason, we need algorithms that just run faster. And if we're in this league of these other languages like C, C++, in my experience, and I'm not an expert in all those languages, so you can disagree, but yeah, I think in general it's more readable. I prefer much rather read code written in Rust than written in C. I think Rust focuses much more on your problem and much less on the computer or the hardware problems. I think C focuses much more on the, let's say, the hardware problems, or how hardware sees things, or how you need to deal with hardware. I think it's faster to develop. Of course not if you have 10 years of experience in C++, that's surely on 0 in Rust. But in general, like considering like good developers, experienced developers in both languages, I would say that Rust should be faster to develop. I think the documentation is great. I don't know that much about the others. Well, C has great documentation. It's named the C programming language. I think it's a 100 or 200 page book. I think that's all what you need to know about C. Then the problems come from other parts. But I think the compiler is extremely good, and extremely good at highlighting your errors, not only on the kind of errors that it catches. I think it's one of the main assets of Rust, but I think the compiler is extremely good at telling you what you're doing wrong. In many cases, the compiler will tell you the exact solution to the problem you're having. It's quite able to detect like what you're trying to do, and because of what you're doing, and give you the correct solution. And I think that also it's extremely helpful, and in some cases you cannot take it for granted. In the Python world, it's also pretty much the case. I think the Python exceptions are in general quite well designed and provide a lot of information on where things are failing or what is failing. And yeah, probably the one that you will be hearing the most is like memory does not leak. That's not 100% true, because there is something called unsafe in Rust that you can use, like you can manage the hardware with a bit more power, you can manage the hardware a bit more directly, and that would be closer to what you do in C. And it might make your code more complex than that, but in many cases you need to do that, and actually we'll see an example of that. And in those cases, like memory can leak and it's your responsibility, but in most cases, assuming that your code is only 1% unsafe and 99% safe, then it makes your life easy because you don't care that much about memory leaks, except for this 1% that you can test pretty well and put a lot of focus on it. And the 99% Rust, the compiler is gonna basically promise you that this is not gonna leak. So I think that's one of the best things if you develop in C. That's one of the problems, like making sure that when you are managing the memory, the heap allocated memory, to be more specific, like that you are basically cleaning up after yourself, that any memory that you book, that any region of the memory that you say, I want to store data in here, that then you go and say, like, I don't need this anymore, please give back this memory to the operating system for any other process to use. And if you don't do this carefully yourself, like, you will end up in memory leaks, and C or C++ will let you do that like pretty easily just by forgetting to free the memory. In Rust, the compiler is going to make sure that you don't forget about that. It's redesigned the whole language just to make sure that this doesn't happen. And that comes, of course, at a cost. The compilation would be slower, and you need to learn new paradigms, but then you avoid all these problems that I think it's a lot of time spent on those when you're programming at this level. It also does not access invalid memory, kind of like for the same reasons as that the memory doesn't leak. Rust forces you to think or to deal with memory in a very particular way, designed so the compiler at compilation time knows that your memory is being used properly, so that you are not doing things that you shouldn't be doing with memory. And when you're having memory, your memory will be freed when it's needed, and that your memory won't be used when it's not yours anymore, when you freed that memory. So I think it also has a great system for generics. So I think that's also a great advantage. I think generics is when you have different types of data function that can apply to different types of data. For example, here we're going to be using integers, and integers you have different sizes. You can work with 64 bits, 32, you can work with floats. So Rust manages in a way that it's not super intuitive at the beginning, but I think it makes a lot of sense. It's not reasoning that much about types, but when you're implementing a function, you say, this function is expecting a parameter that it's able to be added to something else. And just by that, you will be able to use it with integers that, of course, you can add two integers together, by floats that you can add two floats together, and literally anything that can be added, this function would be able. If the function is implementing a sum between two elements, the only thing that it needs, and the compiler will take care of making it for the right types. So it will analyze all your code, check exactly which types that basically are respecting this promise of this type is going to be able to add to another. Well, a value of this type is going to be able to add to another value. And if you're doing that, basically you will get all the generics for free. All the generics, it means repeating the function for every different type. And I think it was also interesting to see that in Python, if you have code that it can fail, and fail in this case, I mean raising an exception, you are opening a file that might not exist, for example. Python is not very specific. I mean, you can just ignore the fact that this can fail. And I think that's an advantage in a way, because you can program faster and it makes the language easier. And Python make that decision, and I think it makes our life easier in many cases. But in some other cases, it's a problem. I think particularly when you're programming at lower level languages, and Rust, it's designed in a way that doesn't have the concept of exceptions. It builds them with some other structures in the language, but it's always forcing you to reason about them. So when you're writing code, you cannot have a line that just breaks. Like the language is designed in a way that it will make you specify what to do when this fails. So I think this is also a pretty nice thing. I mean, it might add a cost when you are developing, but I think most of the time, and you can disagree on that, is not spent that much when you're writing the code. I think writing the code is fast, is when things are failing, and particularly when things are failing in production much more than in your machine, when the problems start and where a lot of the time of a developer is spent. So I think Rust is extremely good at preventing all those things and moving a lot of the problems to before compilation and letting the compiler help you in that. So in a sense, like the Rust compiler is your best friend. It's going to help you a lot, make your programs reliable, and it's your worst enemy because it would be kind of harder than other compilers to make it happy. But in general, I think it's extremely good choice of a language. There are many people who love it. It might not be you. Like that for you to try and experiment. So we're going to now go for the Rust part of it, and we're going to do a bit following the same example, but now we're going to do it with Rust. We're going to do it independently of pandas first, and then we're going to connect both things together, what we did before with pandas, extending pandas, and the function that we implemented in Rust. So everything is going to converge at the end. For now, just forget about pandas and just implement. Like Cargo is the default tool for Rust to compile, and well, it's not the compiler itself, it's just a tool around that it helps you create a project. It will provide a template like a cookie cutter for a Python project. It will basically give you, just by saying cargo new counters, or feel free to name, of course, the program whatever you want. But yeah, like cargo new counters will create like all the files that you need in the project. So it will create this default for you. And actually it will be a hello world example already. So you can just immediately run. And to run it, you have it here, the cargo run. So immediately after that, if you run it, you should see a hello world. And then you would be able to go to these directory counters. That it's the project that you just created. And in the source directory of this, you will have a main.rs that will be created for you. And there you can implement that. And the idea is that you create a function con5s, the same that we've been implementing, and that this one, it implements like this counter that we already implemented. And then from the main function, this is the one that will be executed, you will be able to call this function. I said with this number, of course, feel free to use any other or try with others, but yeah, if you call it with 5 of i's, you should get the result here, the number 2 here, you should get it there. So I'll give a bit of time. If you're new, like in Rust, you probably can just quickly check. Stack Overflow will probably give you exactly how to do this. And I think it should be pretty easy, but I think it's better if you try it by yourself, even if you are not, I assume. Is there anyone who already knows Rust, who is a Rust programmer here? Anyone? Okay, I see 1, 2. Okay, cool. Yeah, we won't see too much of Rust, but at least you will get an intuition, and you will be able to have, based on very simple examples, but you will be able to have an opinion on whether some of my valid points on why I like Rust are valid for you or not, whether you find it more readable or whether you find like the compiler message is nice. And if you have any question, just please let me know. I'm here for this. Sorry? Yeah, please. Yeah, so you should have the same exact thing as in the screen. So you should have this number 2, besides like the compilation information, like the logs, you should have the number 2. It's more for you to know that it's working, but yeah, you will build on top of the function much more on the main call, but I think it should still be useful. If you don't have the Rust environment already, every operating system might have different ways or things, but in general there is a software named Rust app. If you go to the Rust website, you will see that's the recommended way. There is a script named Rust app that should give you a Rust environment pretty quickly with already cargo and everything. Absolutely, yeah. As I say, like if you have any question, and any question means like any problem that you might have, like with the environment or whatever, happy to answer questions. Or, yeah, Marco is a good Rust programmer, so he will be able to come and also check your exact problem.
Yeah, just raise your hand if you want someone to come and take a look if something's not working.
Oh, that was fast. Anyone else having issues? Next time we'll bring pandas stickers, so you can get one if you ask questions. And how many of you managed to implement this already? Anyone? A few of you, cool. How many of you managed to implement to run the hello world? A few more. Should we give a couple more minutes and I'll show the solution? Also, if anyone hasn't used Vim before and followed these commands exactly, and you cannot leave Vim, let me know. The solution is usually buy a new computer, but there might be others. Cool. I'm going to show the solution just for the sake of time. I think it would be better if we had more time, so you could find the solution yourself. But yeah, we're going to move. That's what, I mean, doesn't necessarily need to be your own solution, but that's what probably I would do. And I think that's probably one of the shortest and probably more readable. I mean, you can implement a loop. And as I said, this can be a bit mysterious if you are new to these things, but when you are in the Rust world or C world, loops are totally fine. When you are in the Python data world, loops are not fine. Loops are going to be slow. I mean, when I say that are not fine, it doesn't mean that you cannot use them. If you have a data frame with 100 rows, use whatever it works for you. It's like, don't let anyone tell you, oh no, you should never do that. I mean, whatever it works for you is fine. But in general, if you have like something like 10 million rows, and if you start to do real things with this data frame, like if you apply any loop, it's going to be very slow. Like, and very slow can be 2 up to 3 orders of magnitude, depending on what you're doing. So yeah, but in the Rust world or the C world, loops are totally fine. And there are reasons, and we can go, if people need to, we can go on why is that. So yeah, I think as a good heuristic is like which world where you are, and also that's the reason, because the apply function that we've seen pretty much iterates like in the Python world for every item, and that's what it's slow. And in this case, we're moving things to there as well. So here, it's like if you want to iterate over the string and check if every value individually is a 5, maybe the compiled version that you get out of this from this Rust program is pretty much the same as you get. It might be a difference, but this difference shouldn't be that significant. While in the pandas world, it would make a big difference in general. Is it clear? So if you want to copy, particularly the first function, I hope it's fast to copy. We are going to build on top of this. So the next exercise will need this function. If you want to copy, that would be great. I see more or less everybody is done. Otherwise, I can go back. Let me know, and I'll go back to this slide. But yeah, now working with vectors. What's a vector? It's always the same. In some places, they call it array. In some places, like Rust, they call it vector. In some places, like artificial intelligence, they call it tensor. In some places, they will call different things. But yeah, the general idea now is create a new function. We'll still have main. We'll still have the conf files for individual value. And now we are going to implement a new function that it's gonna for a particular vector. And this is the way the comment here is the way that you will create like a vector, the equivalent of a Python list. Like this is how you would create it in Rust. And what we want is to have a function that receives a vector and applies the previous function, calling the function to every element on that vector. Is that clear? So it's just pretty much implementing the loop, if that's clear, and just receiving the whole data and making sure that you apply to every individual element of that vector in the Rust world, or list in the Python world, or array, tensor, whatever. Cool, I'm going to move forward. I assume many of you didn't finish. I don't think that's as trivial as some other things, but yeah, I think it's probably better if you are interested that you have a look at vectors in Rust yourself and get familiar with the syntax and that. And we have a bit more time for the rest, the part that we start connecting things with pandas. So this would be the solution, and as I said, like you will have others that can be as valid as this one. This is the one that seems the most obvious to me, but that doesn't mean that it's the one that you like the most or the one that you decided to implement. And yeah, since I assume most of you, at least, or all of you are familiar with Python, I don't think this comes like so as a surprise. Like map would be the same in Python, even if we wouldn't have a collect in Python. It would be just like we would usually call the list method to make this iterator. This is just like working with iterators in a very similar way as Python. So what it will be doing is converting this vector to an iterable. Imagine exactly like a Python generator, and then doing a map. A map is just applying a function to each element. That's usually it's the same in pandas. I shown the apply method, but actually there is another one named map that it's pretty much the same. And they shouldn't probably, but they are pretty much the same, even if map also accepts a dictionary and you can just use it to convert from a dictionary instead of applying functions. But if you call it, it would be the same exact thing in pandas. And then collect means literally convert this thing again to a vector. So if you're familiar with data generator or a Rust iterator, it means that it's something that it's processing. It's just a stream of data. Nothing happened. It's just like a sequence of actions. And then when you say collect, and when you convert like a generator to a list in Python, what it happens is that all this basically gets executed and gets into memory. So this is pretty much what we're doing here. And we are just receiving this vector, iterating, creating this sequence of operations that it's pretty much one, and generating a vector again, which is memory data in memory. And then for the call in print, it's just changing. It's same as before. Well, it's not same as before. There is one detail here. If you see the println, before it was just the curly brackets that I used to print, and now it's like this colon and question mark in between. Like that's like the way Rust defines things. There are two ways of objects can have two different ways to be expressed. It's a bit like the same. You can think of it as when you are converting something as a string in Python, or when you're calling the representation method, the REPR in Python, that a class, for example, you would be able to call and see like the memory address or the name of the class and that. Well, if you are printing, you usually would like to print more things. Or if you think of bytes in Python, for example, the representation would contain the B and the quotes, while if you just print, you convert to a string, you will just only get the content of it. So yeah, you can think a bit about that. So the curly brackets are just to print things like an integer, things that you can print directly, and this colon question mark, it prints things that you have a representation, that you have a function kind of thing that represents. You're not seeing the actual thing, you're seeing a representation on how it could look like. You can think a bit about this. It's what in Rust is called the display and debug traits. If you want to find more information, not something that we're going to see in detail here, but I think it's a pretty nice feature when you get used to it. Cool, so hopefully everybody had the time to copy, because we'll continue building on top of this. But now I'll give you a short break of exercises that will come after this slide again. But for one slide, you have a bit of a rest. And I'm going to talk like, now what? Because I think now we saw how to extend pandas. We already created a pandas extension that we're able to call whatever we want. And we also are able to take like a list of numbers that in the pandas world, that's a series. In the Rust world, that's a vector, but they are pretty much the same thing. And we've seen how we can do operations in Rust, given a vector, how we can compute another vector with whatever we want, in our case, our example function. So now we had a big problem to say. We created 3 different problems. One was extending pandas, another one was to implement a fast and efficient Rust implementation of our algorithm, and now we have the 3rd and last problem, that it's putting everything together, connecting one thing with the other. So here, this is the example, this is the code that you just wrote yourself. And as you can see, like in this accessor, my implementation was calling self.series.apply and calling apply, as we did in the first example before starting the proper extension. But if you see in the comment there, what we could do here, and we will get our extension ready, it would be just calling the Rust wall, whatever is that, whatever we can access this magic wall of Rust from Python. Like if we can access it, we can call this function that we implemented. This is the function that you just implemented, and we can pass our series. That of course is not exactly our series. It's going to be a vector, what we need in the Rust wall, but it's pretty much the same thing. And we already implemented this function. So this is the function that you just implemented. So we just need to be able to call it and to pass the parameters. So as I said, we had one problem that we converted in 3. Now I got one problem that I'm going to convert into. First, how we call this function, and then how we provide the parameter to it. So we need a bit of theory for that. We need to understand a bit like how pandas internals work, and that would be kind of shortly, even if it's a huge mess, I would say. But I'll just show you very quickly how that works. Then calling libraries from Python. And in this particular case, I don't say calling Rust libraries in Python because it would be pretty much the same as calling a C library. If we learn this way, we'll learn not necessarily any language way, but we'll learn more than the way that you would probably use for C++, C, and Rust at least. Then sharing memory is the next part. Like when we're able to call this function, we don't only want to call this function, we want to call this function with the data that we need. And then this is probably we won't have that much time for that, but if anyone needs it, talking a bit more about memory, what's in memory in a computer, that I think it's something a bit magic, and we're going to get pretty close to those details. So I have some slides also for that we might or might not cover depending on time and what people need to know. So the general architecture, that's more or less how I would describe what's going on here, just to understand a bit more the concept. The main part is this blue arrow in the middle. That's the execution of our program. This is pretty much the Python interpreter that we called, and the Python interpreter checking our our script and running every line of code at a time, right? That's more or less what a Python script execution would be. And I have 2 things here, not very clear, they don't look like that much as Python, but the first one is I'm creating a data frame, and by creating a data frame in the Python wall, I see this variable df, and I can do things with that. That's how we work with it in the Python wall. But what is happening in the computer itself, in the memory, it's actually putting lots of zeros and ones in some parts of our computer's memory. And we have these 2 points of it. It's kind of like the same thing, but we have like what the user sees is like our Python code to say, and what the hardware deals with, that it's our memory representation. And then after we created this data frame, what we'll have is this FFI call, that this is calling what I named before the Rust wall, or in that case would be more I think a more appropriate name would be the C wall, because basically Rust would be called as if it was C. So as I said, like it would be the same as C. FFI stands for foreign function interface. It's just literally an interface to call functions that are defined in a foreign language. So in this case, it would be Rust. So here in the left, we have our source code of Rust that we write, and then we compile it, we get this library, and this is what we'll be calling. And the last part is this dotted arrow that you see. That is when we call this function, we want to be telling that this function needs to operate on that data. Is this more or less clear? Is there any question? Okay. I'm not sure if that means that you are ready to board to follow, or everything is super clear. Hopefully everything is super clear. Feel free to come. We can come back to this slide later because that gives you more or less the whole picture. If this is not clear, it would be a bit more difficult to understand exactly what we're doing after this. So we are going to start by this part, like what the user deals with and what the hardware deals with. And the first part is like pandas itself. And pandas, if you are familiar with these Russian dolls or Matryoshka rolls, I think it's the name for it, you will be, if you like them, you will probably like pandas, because in a way it's pretty much the same. And if you want to know what's inside pandas, like the general idea that you have here, this is not very accurate, but I prefer to be a bit wrong than too complex or not clear at all. So yeah, there are some subtle things that you could say about this, but the idea doesn't change much. This is pretty much what, when you have a data frame, how you actually get up to the memory. And yeah, data frame, I think the first part is the most obvious one. A data frame in general is just like a sequence of series, like a series is every column, so basically from a data frame you can extract a series, but then like pandas supports many different types, many different things, there are like lots of things going on, and because of that it starts wrapping like the data into many different structures that it's the ones that we deal with when we program the pandas internals. So start by this series, then we'll have this block manager that it's kind of like the manager of our blocks of memory in this case, and then we'll have a specific blocks. We have different types, and here I have two different series that are different types. As I said, like pandas in general deals with two different kind of data. One can be NumPy arrays in memory, and another one can be arrow arrays in memory. So depending on which one you're using, and that's your decision, and if you don't know about those things, it means that you've been always using NumPy structures. If you've always been using NumPy and your strings are slow, it's probably a good time to learn about arrow structures, because arrow structures is when you get your types in arrow. Like string operations in pandas are probably one order of magnitude faster. I don't know exactly like how fast they are, but they are much, much faster. So if you're working with the strings and you never heard about arrow, it's something that we're going to change eventually. At some point, we're going to make that, and I think that some point is pretty soon, but yeah, we're going to make like you get the strings, the faster strings by default, but for now the approach of pandas is being pretty conservative, so since we develop something new, we take a pretty decent amount of time for some users to be able to experiment, detect bugs until we make it the default. But yeah, as of today, basically, if you want to use fast operations on strings, you should be using arrow types. We also have integer types in arrow, and we have in NumPy. I don't think you might care that much about those at this point, but yeah, just for you to know how this works. And if you have a data frame, or in this case, you have a series to access from the data frame to the series, you know how to access. You just get the square brackets, and if you're using pandas, you do that all the time. But from a series to get the internal data, the internal representation, and internal here is not too internal yet. It's internal up to all what we can go into the Python wall, because then things become Fortran, become C, become other things, or C++. And then from the Python wall, we lose track of what's going on. We can just play with the Python objects that this library is exposed. But yeah, like the more internal thing that we can go is an NumPy array, that it starts to be like very close to the memory. And from the arrow side, we can go to this chunk array, and then from it, we can take every chunk, and every chunk would be an arrow array. So exercise for you. We're back to the exercises. Pretty simple, this one, I would say. Just create a function that we'll need a bit later. Get internal structure that from a series gets the internal structure. And the internal structure, as I said, means the most internal Python structure that you can get. That would be an arrow array or a NumPy array. I implemented for both, so you will have the solution for both. If you are unsure, and since we don't have unlimited time, I would say probably go for NumPy. I think NumPy might be a better one. Just forget about arrow for now, but yeah, I think it's pretty useful for you to know that there are two different types of data memory representation, because if you ever program a extension in Rust, you will have to either program for one of them only, or make sure that you support both of them. So that's the thing. So yeah, like I won't spend too much time. If you want to just write this function, and I'll just show the solution in a second, which is now. And I say my solution is more complex because I'm using like a function for that it detects whether it's NumPy or it's arrow. In your case, you probably want this block content, this line, this first line. It's probably what you want your function to return. If you do that, it will work for NumPy, and for the sake of this tutorial, you would be fine. So you probably don't need. But yeah, I think it's good that you see that from a series where I can check the data type, I can check which type of the data type it is that series, know if I'm in data that it's actually an NumPy structure, or if it's data that it's an arrow structure, and knowing that, I can go and access the memory object in the Python wall. And in this case also, yeah, probably worth mentioning that in the case of arrow, the memory can live in different chunks. So you can have like a super long array that has been allocated in different cases. So you had a CSV and you didn't want to allocate all at once, or maybe it's a data that keeps growing over time that you're just generating, and you can just like do it in chunks, and an arrow structure support that. So you might have, in this case, I didn't implement it multi-chunk. I just made like an easier choice that was like, I take the first chunk, and if there are more than one chunk, actually, I just fail for making sure that things don't fail silently, which usually it's only the root of problems. So cool. If you copied that, going back to the part that we call extensions, and as I said, like this would be C extensions. In this case, it would be a Rust extension, but yeah, whatever extension that you have compiled that follows this interface. And the first thing we need to do, it's like that we didn't do, is we need to make our Rust program, it's like a binary. It's something that Cargo was doing that for us, so it was a bit magic, but what you got inside of Cargo is you got a binary file. In the Windows world would be a .exe. In the Linux world, it's just like an executable file. So you got that file. There is a target directory in your project if you're interested, and in this target you should have another debug directory, and in there you should have this binary file that you can just call. And if you just call it, you will receive whatever you implemented before that was printing this array of numbers. It was like printing 0, 0, 1, 2. So this is useful in some cases. If I'm doing my own application, if I'm creating a program that I'm going to call, that's pretty much what you would be doing. In this case, this is not what we're doing. We're not going to use our program directly. What we're going to do is call our program from another program. In this case, a Python program, but that's irrelevant. So this becomes a library. It's different concepts. Rust support both. When you create the project, you can say that it's a library, and it would do this for us. But yeah, the general idea is if you add to the Cargo toml, you add this, what you're seeing here in the top, like you will be making that our program is not an executable anymore, but it's a library. And this library is what we will be calling. And it's worth mentioning this crate type because Rust supports at least two different types of compilation. One is compiling for the Rust world. If you are building a program in Rust and you have extensions, like imagine pip packages, the equivalent of pip packages that are called crates, you would be able to take your Rust program and say it depends on this, it depends on this, it depends on this. It will take the different libraries, the compiled version of these libraries, download it, bring it into your project, and compile everything together. So that's the default version of doing libraries in Rust, is thinking about other Rust developers. In this case, this is not exactly what we're doing. We don't want other Rust developers to use our library. We want, let's say, Python in this case, or other C libraries to call this. So when we change this crate type to cdylib, we are telling, okay, compile this in a way that it's understood or it can be accessed following the same ABI, it's the technical name, application binary interface, and it would be using the same as C libraries do. So we'll be able to call it as if it was a C library, and as far as I know, it should stop making a difference whether we implemented it in Rust or it implemented it in C. It shouldn't make it actually makes some differences. The size of a Rust program in general would be much bigger, the size of the library or the exe. There are reasons for that, but yeah, like there shouldn't be a significant difference in terms of who is calling this library. And the second thing is this main to lib. So before we had just this function main, Now we don't want to have a function main that is the entry point where you're calling a program. We want to create a function that we can call. And we need all these things. And just the function and the name, that would be the same as main with a more descriptive name. In this case, we say it's public. We need to say that because it's going to be our public function. We could have functions that are not part of our public interface in this library that we're developing. And extern C, it's a bit the same as the create type. We're saying that this library, this function is respecting this C interface, so we are pretending to say we're impersonating C here, and it's all what we're trying to do, and say, okay, I'm implementing this in Rust, but actually I want to make it in a way as if it was C. And finally, the no mangle, it means that when you are compiling things, what it would do is it will change the names to add some prefix, add few things here and there that they might be needed by the Rust. It will make the life of the Rust compiler, the Rust like dependency system easier, things like generics or things like that. It will might create the same function with 3 different names depending on the data type that you are using, like things like that. The no mangle, it means like, no, don't change my name, because if you change my name and I don't know what it is, I'm not able to call this function, because I won't be able to know what's this name. Of course, I could go and introspect the library, but yeah, like we just say, like no mangle, and we make sure that the name is this. Did you manage to run cargo build? Yeah.
So should the function still print?
No, yeah, good question. The question is if the function should still print. The answer is no. Now there is no entry point. When we're not calling, actually, the cargo build is not the cargo run. We're just building, we're compiling, and we're expecting someone to call our library. In the previous case, we're building a program by itself, and then cargo run is building, and after building, it's running. So yeah, very, very good question. It shouldn't print anything, but it should be happy. The cargo build should be happy and should compile.
I mean, the println function.
Yeah, just wait a second for the mic.
Yeah, previously in main, we had println in the end. Should it be here still?
Okay, yeah, please. Yeah, so for now, since things are going to take a bit longer until we have our final version, if you print, we'll be able to know when you are calling this from Rust that it's working, basically. So we'll be able to know that it's working even if we are not returning anything initially. So yeah, leave the print as it was. Only these changes on the slide. So okay, just for your information, and I think it's probably very relevant information, there is another obvious way, at least, to do these things. That this is not the one that I chose for this tutorial for different reasons, but it's a very smart thing to do in many cases. And it's, for example, what Polars is doing for binding Python with Rust, and it's using this Pyo3 package. The website is this is the URL, even if I'm not sure if it's super clear. Like Pyo3, it will do most of these things that we've been doing. It will do it for us. It will create some interfaces, and the nice thing is that from Pyo3 we would be able to access directly Python objects in Rust. Our library, the way that I implemented this and we're following in this tutorial, it's totally agnostic of Python. We could use a C program and make our C program call our function, and yeah, there is nothing Python about it, and the whole Python world would be ignored. In Pyo3, it's different. Pyo3 is assuming Python, and the nice thing is like you can also implement functions, Python functions that you will be able to call from Python directly from Rust. So it's a different approach. It's basically let's say that the border between Rust and Python is changing. I think for many use cases, Pyo3 is probably, and if you are starting, probably it's what you want to use. But I think it adds a lot of magic. So I think for this tutorial, it makes more sense that you understand what's going on. But then just go to Pyo3, and Pyo3 you are able to pass like directly a pandas series, and everything that we've been unwrapping in the previous slide of the Russian dolls, you would be able to do that from Rust if you want. I don't think that's very smart, but you would be able to do that, and you would be able to deal with other objects. For example, a Python list is something that makes much more sense to be able to send it to Rust, but Rust doesn't understand Python lists, so Pyo3 is the gap, is the library that fills this gap and basically is able to understand Python objects in the Rust world. So yeah, I really want you to know about Pyo3. I won't continue yeah, I won't show Pyo3 in here, but yeah, it's something that you surely want to consider if you are going here. So finally, calling the library, well, finally there is still one more exercise after this, but yeah, we're getting closer. Calling the library from Python, there are different ways to do that, but yeah, we can use, there is a library in the standard Python standard library. You don't need to install anything, that it's called ctypes, and in ctypes there is this function cdll load library. That would work for Linux for sure. I'm not sure for the ones in Mac if that works or it's a different one. You might check the documentation for that. If you're in Windows world, it surely doesn't, it will work, but it's a different function. I'm not sure exactly what people are using here or what you're doing, but yeah, you might want to check the documentation, which is the exact function for the operating system if you're not using Linux, or a better option, just migrate to Linux. There are no reasons to use any other operating system in 2023, I would say. So yeah, and the general idea is that you should be able to call your Python script where you implement this call with this function, and you would be able to yeah, like call it and see the result printed. He was asking before if we should keep the print. If you keep the print, you will be able to see it printed here, which should be pretty nice. I think just for the sake of time, I'm going to go directly, yeah, and I think it's probably worth mentioning, we need this environment variable. Pyo3 would take care of that, or if you build things for a package manager and that, you can take care of those things. But in this case, since we're building things like from scratch, you need to tell let's say the Python interpreter, and more than the Python interpreter, any program in your system where your libraries lives. So this is what this environment variable LD library path is doing. Yeah, can you wait for the mic, please?
Can you show the file librs, because we just showed a fraction of it which doesn't work? The full file, the whole file librs, the content, because all this content, it gives me a lot of compiler errors. Can you show the content of the librs?
I don't have the, yeah, I have it from the one from before, which was this one with the...
As soon as I apply this pragma or whatever it is, it's just no type, everything, a lot of errors. Because I don't know where to put these things, the extern pub and stuff.
You should have on top of, well, you should rename main, then prefix it with pub extern C, and then have the nomangle on top. Yeah, sorry, I don't have a slide. I didn't prepare a slide for that.
There's a lot of...
Yeah, we can, yeah, I think we can skip, yeah, like, you can continue later because we don't have too much time anymore for this. Yeah, sorry about that. So yeah, this would be like what you would be calling. It's just like you just import these C types. As I said, you don't need to install it. It comes in the standard library of Python. You load the library. Basically, this first line of the return, what it's taking is like this library, bringing it into memory, to say, loading this library. And then this object that we're getting from loading this library, it will have an attribute for every function that we defined in there. So if we call this function, that is the one that we implemented, we should be able to call this. And as I said, we need this LD library path. Otherwise, when we're saying here, just load the library by the name, that's how the whole Unix world works. Like you define only here the name, not the full path, and then you need to have this installed in the libraries in the system. So yeah, if you do that, you should call. So now we know already how to call things from Python. So we already basically connected the two walls, what we did in the pandas extension, that of course you can go there and start calling from there. But there is only one part missing. We've got 5 minutes for it, that it's passing the data to Rust. And this is probably one of the most interesting parts of this whole thing, even if it comes at the end and it won't be too long. But the general idea here would be that I got this get internal data that it's getting me close to the memory representation. And when we are close, and I'm going to focus on NumPy, when we are in NumPy, we have a way to extract like the location in memory of this array. And this is what I want to send to Rust. So in the case of NumPy, we have this attribute of the NumPy array that is the under method array interface. And here you would have all the information that you need about where this data lives in memory for other projects to use. In the case of PyArrow, it's pretty much the same, but you have this buffers method. So what we need to do is to pass it all this information to to Rust. And I'm going to go a bit back to this slide, because here what I'm going to pass, the thing that it's going to be in this pink square over here, it's the 03 that you see there in gray. It's the memory address. So the memory in the computer has a number. It's numbered, so you know exactly what's the position of everything you store there. That's what in C in general it would be called a pointer. You can call it memory address. Should be the same concept. And what I want is to say that I'm not going to send all my data to this function. What I'm going to send is that my memory is in the position 03. And this position 03, then this library should be able to go to memory, knowing where it is, and accessing that memory would be able to read all the data. That's basically what we want to happen. So here I was calling, and here this is what I want to do. I'm going to show the solution directly from the Python wall. I just get this array interface, and I say it, and it says it just has a dictionary structure that you can get the data. Those are some pointers. This I'm just casting to the ctypes wall. I'm getting from the integer representation of it to a pointer in ctypes, and I'm providing this pointer as a parameter. So it didn't change much if you see. I'm just getting the memory address from NumPy. I cannot pass it directly as an integer. I just need to convert it. But once I'm converted, I just call the function with this parameter. Of course, in the Rust wall, we need to expect this parameter to be received. So we need to also change Rust. So this is the function. Yeah, Mike, I think this is what you wanted before with the new change, with the parameter added. But this is the code you were asking for. So this is the final function of what you would have in lib. So this is what you had before, but instead of calling from a vector that I'm defining myself, I just get that pointer from data, and here there is this concept of a slice, that the slice is like a view on some memory. I'm saying, okay, this is integer 64, there are 4 elements, and I'm just getting this into the Rust wall. So I'm printing this data after calling the function that we implemented before. Is this clear, more or less? Was this too fast? So, of course, this is not done. It's kind of done for the tutorial. I will wrap up, but this is the general idea of what we've been doing. Of course, there are a few things missing, like in 1 hour and a half, as you've seen, we don't have the time to really implement the full extension. The first and most obvious thing, of course, we don't want to print on the screen. What we would like is to return this data to pandas. And the concept is the same, like the code changes a bit, but the general idea is true. We're going to create the data, in this case, in the Rust wall. We're going to create a vector and then take the memory address of this vector, and this is what we are going to return to the Python wall as a return of this function, and the Python part will know that this memory needs to be like obtained as a NumPy array, if that's what we are using. So, and also the number of items is something that we cannot take for known. I mean, in this case, we know everything because we are gods. We are our user, like the producer and the consumer, so we know exactly what we're going to receive. In the real world, we won't know the number of elements, so we should get that also from this array interface. It will also say how many elements you've got. You can have them and pass this as a parameter. And I think we're getting close to the end. Just this is like my last slide, or I think I have a very similar one. The general idea is that when we're passing all this information, there is Apache Arrow that, as I said, is like the alternative that we're using for NumPy, like has a mechanism to provide all this information for us. So all this, well, NumPy also does that, but the problem with NumPy is that it's mostly designed for numerical numbers. Arrow allows you to have dictionaries, to have categories, to have strings, to have lists in a single cell of a pandas data frame. So it's a bit more, it's more extensive. For numbers, if you're only dealing with numbers, NumPy is fine. Since that's usually not the case, Arrow is what we are migrating to. And Arrow implements this way that we have some group of data basically that we can put into memory, and instead of passing the pointer to the memory, we pass the pointer to this structure of metadata, and this structure of metadata knows where the data lives, which is the type of the data, what's the length, and that. If you are a C programmer, this is pretty much, there are actually two structs. This is for performance reasons. It could be one. But yeah, we have like the format in particular is pretty relevant, and then we have the length. This is one of the things that we were missing. And these buffers, it tells you where the memory is. And actually the memory can be in different places, because Arrow, as I said, it supports a bit more complex types. For numbers, things are extremely easy. For other types, things become more complex, like strings or even dictionaries of strings or whatever. So this is like the interface that Apache Arrow extends, and this is probably the one that you would like to use in a real case. Like now using the general idea of how you would extend in Python, and then you would use this. And this is everything I've got. I think we're just in time for the break. I think it's break time, but I'm happy to take questions. If anyone has anything, just wait for the mic, just show hands, and there's one there.
There seems to be a lot of boilerplate with all the pointer stuff back and forth, and it seems to be very similar for all the functions. Do you see any way to kind of make it easier than you don't have to write all the boilerplate all the time?
Yeah, I really like this question. Yeah, that I think we should make a framework that the final user just implements like the very internal part of the function. This is not implemented yet, so that tutorial would be much easier to teach and say like, okay, just write your function in this way. Probably we can just wrap it in a macro in Rust, get some dependency, and get everything done for you. I think it's not gonna be like that simple. I think we need to get like both code in the, you will have to implement extensions both in the Python wall and in the Rust wall. But yeah, we can surely like simplify lots of these things. And also like Arrow has implementations in Rust. So all the FFI part, all the dealing with the structure, loading the data is something that already there are implementations and you wouldn't be doing manually. For the tutorial, I wanted to be very clear in the, not calling functions that we don't know what they do, going to the very basics so the concepts are clear. But yeah, I think it's a very good question, and hopefully we end up with something. And yeah, something that's interesting also is like, here I've been talking on pandas and Rust. There is no reason why we couldn't do this exact same thing in polars. Polar is totally backed by Arrow. So if you have pandas data backed by Arrow and you have polars, you can implement your extension one and you would be able to use from polars. And I don't think it would be, I'm not an expert on that area, but I think even from R, you could implement things like this. I think this approach should be able to be extended for anything. But yeah, we should hopefully make things easier for the user, have like all the boilerplate, make it in one library, and let users implement extensions super easy. Not sure if that's going to happen or not, but we should totally do it. Any other question?
Well, first of all, thank you for your presentation. It was very good. Could you just quickly go back to the slide with Python code for calling the numbers?
This one?
Oh, yeah, okay. So I just missed the last part. So you load the library and then you call the function.
Yeah, the load library and calling function is exactly the same thing. The only difference that we added is the pointer parameter here. And the pointer parameter, we just get from NumPy. NumPy is giving it us. The only thing that you need to transform from Python wall to C types wall. That C types is kind of Python, but with C types. I think that's the name is pretty good, actually.
Okay, thank you.
Yeah, welcome. Yeah, one more.
So what kind of speed up do you expect typically, and when is it actually worth investing the time into all this instead of writing Python with NumPy code, things like this?
Yeah, very, very good questions. The first one, for this particular case, I expect one order of magnitude. I think this should be as fast as polars and probably a bit more. But yeah, I didn't test exactly, but yeah, that's more or less what developers would be doing. There are many factors there because you can also parallelize this. In Rust, it's extremely easy. Like with, I think, pretty much 1 or 2 lines of code, I would be able to run this code that we've seen in parallel, which is extremely amazing, but not always a good thing because you might be parallelizing also column-wise in a data frame. So I'm not sure if parallelizing like for a single array is necessarily a good idea if you don't know where this is going to be called from. I think for other problems, it will depend on your use case a lot. I would say that in some cases, it's like 2 orders of magnitude would be something very reasonable to obtain. It depends on how slow Python is, to say what's the overthread on Python. Of course, if you have a function sum implemented in pandas already working in numbers, I don't think you can expect much speed up. You will get something different for sure. It can be a bit slower, it can be a bit faster. I don't really know. In the case of when this is worth, I mean, I think the complexity of the whole system is pretty big, and as I say, like I think simplicity should come before performance, and that's of course like subject to, depending on what's if you're in high frequency trading, like performance is everything and simplicity doesn't matter, and if you are trying to compute an algorithm that it's like so super slow, like performance is everything because otherwise you cannot run things. So I think it depends. I would say in terms of performance, don't solve problems that you don't have. Don't try to make things faster. I think quoting Donald Knuth, like premature optimization is the root of all evil. So don't get into that if you don't need to. Find other simpler solutions. As I said, Numba can be a good solution too, and it's surely a simpler, even if it comes as a cost, certain complexity, and certain things of just-in-time compilation. So it depends a lot, but yeah, don't do this just because, oh yeah, I don't like the pandas sum anymore because my Rust version is going to be. Rust is not providing that much compared to C or Python, that is what we're using mostly in Python, or they're using in NumPy. Like, it's just like, it provides the simplicity of being able to, when Python is slow, being able to develop faster. Cool, there is one question there, I think.
So would this work on any series? So for NumPy, what can happen is that I can easily have a NumPy array that isn't C-contiguous anymore, right? So aren't you playing tricks a bit by initializing it right there and not pulling it from a more complicated setting?
Absolutely, yeah. Yeah, I think I was cheating badly in everything. Sure. You've seen here, just for the sake of people understanding the concepts. I think the red part here is the disclaimer that we're telling. Yeah, like in this particular case, it's not only that you need to provide the data type. I'm saying here, yeah, we should tell Rust which data type it is, otherwise it will just see zeros and ones and it won't be able to make sense of that. But yeah, it's a bit more complex than that because you might have to implement your function for different types. Because in the Python world, you can have a function that receives anything. Everything is a Python object, so you are always playing with Python objects. And as far as the operation is supported by that kind of Python object, you are happy, everything is fine. In the low-level programming, you are telling the hardware literally what to do, and the microchips literally deal with integers, deal with floats, and deal with this type of data. And you need to tell them exactly when you're compiling code what we are dealing with. I mentioned before it was a bit subtle, but I say like that Rust works very well with generics, that it means implementing a function once and being able to use for different data types. I think this comes very handy here, but it of course still comes at a cost. It will bring some complexity, it will get some problems. And as I said, for things for numbers, and yeah, I was cheating badly here. I picked like integer 64 and I could pick like any other integer or float. And that makes things extremely easy. If I go to the wall of strings, that it's a reasonable, simple data type compared to other things that you can have, but it's much more complex than numbers, things will start to grow in complexity a lot. So yeah, like this is like the hello world example of connecting all the dots from the pandas, building an extension, being able to share the data to Rust, and Rust being able to be called from pandas. That was the simple possible example I found. If you go to any other data type, it's going to be harder and it's going to be challenges. But this interface, the ROC data interface, make a lot of this life easier for any type. This is so long, actually we need just the memory address, the length, and the data type. Everything else that you see is just because of the complexity that you can have a cell that is actually a list, and in the elements of the list can be a dictionary. You can have all this complexity on your data, and all this data structure supports that. So that's one of the advantages of Apache Arrow here, that it's going to make your life easier, at least for exchanging the data from Python to C, to Rust. Cool, so I think we're done, break time. Yes, we got past 3.